In this video, we're going to talk about electric fields. So in the last video, we talked about electric charges and the forces that charges exert on one another. But the problem is a charge can exert a force on another charge without touching it, and we don't have a good way to explain how this force acts over space. The electric field will solve this problem. We say that a charge changes the space around it by creating an electric field. Then, when another charge is present in that field, it feels these changes to the space around it from the first charge, or it feels the electric field. So in this model, the electric field is what is actually exerting the force on the second charge. Now, a field is something that fills all of space and has a value or a strength at every point in space. The electric field is what is called a vector field, meaning at every point in space it has a strength or magnitude, but it also has a direction. So you can think of an arrow or a little vector sitting at every point in space. The magnitude or strength of the field influences the size of the force exerted on the other charge, and the direction of the field determines the direction of the force. Mathematically, the electric field is the amount of force per unit charge. The electric field alone cannot tell you how much force will be exerted on an arbitrary charge because it depends on how much charge you put in the field at that point. So the electric field tells you the amount of force per unit charge, and the force felt depends on how much charge is placed in that field. Here we need to make a very important distinction between the charge or charges that are producing the electric field and the charge that is placed in the existing field of the other charges that is the charge that is feeling a force from the field. We will call charges that create the field source charges, and the charges that feel the effects of the field test charges. Source charges will denote with a Q, and test charges will denote with a Q prime. If we rearrange our definition of the electric field, we get F equals Q prime times E, the electric field. This is the force F that is felt by the test charge Q prime when Q prime is placed in an electric field E. Here, since we already know the electric field value, the source charge creating the electric field isn't necessary to find the force on Q prime. Now let's look at the force between 2 point charges that we saw in the last video. We labeled our two charges Q1 and Q2 to distinguish the two, but the force on each charge was the same, so it didn't matter. If we want to look at each charge separately, we can label one the source charge Q and the other the test charge Q prime. If we now write our definition of electric field and plug in the force between point charges, we see that our Q primes will cancel. What is left is the electric field created by the point charge Q. If we take this and multiply it by another charge, we will get the force on that charge due to the field created by Q. We can also write this with 1 over 4 pi epsilon naught instead of K, just like we did before. As we go along and obtain more equations, it's important to be able to state in words what the equation gives you and what each variable stands for, so be sure to make note of these. We'll now look at a way to illustrate electric fields, but first I want to make sure to say charges will never feel the effects of their own electric fields, so each charge is either a source charge or a test charge, and this is why we make this distinction. This is another way of saying charges don't exert forces on themselves, just like we saw in Physics 1 with other objects. So when we illustrate electric fields, we must keep track of which charges are producing the field and which ones are actually just feeling the field, but don't contribute to the field that we're looking for. We said the electric field is a vector field that we can think of as having an arrow at every point in space. Since it is difficult to draw arrows at every point and draw them in such a way to have their length represent the strength of the field at that point, which is what we typically do with vectors, we will instead draw electric field lines. There are rules for drawing electric field lines, and they are the following. Electric field lines go out or away from positive charges and into or toward negative charges. Field lines never cross each other. Where field lines diverge or separate from each other, the field is getting weaker, and where lines converge or get closer, the electric field is getting stronger. And finally, electric field lines point in the direction a positive charge would move, which is another way of saying the direction of the force on a positive charge if it were placed at that point in the field. For a positive point charge, the field lines would move away in all directions, and we'll put arrows to indicate the direction. For a negative point charge, the field lines would look the same, but point toward the charge rather than away from the charge. For both of these cases, imagine placing a positive charge on any of the field lines. Which direction would you expect it to go if the field lines weren't there? It would move straight toward a negative charge or straight away from the positive charge. This agrees with the direction of the electric field. We can also see that a negative charge will move or feel a force in the opposite direction of the electric field, so we'll need to adjust for this whenever we're dealing with negative charges. If we place a positive and negative point charge next to each other, we'll get something more complicated. On the far sides, field lines will look the same, but the field lines closer to the other charge will be bent toward or away from the other charge. You can imagine the field lines trying to escape from the positive charge, but the negative charge pulls them toward it. For two like charges, say two positive charges, we get the opposite behavior. The field lines of one positive charge are repelled or pushed away from the other positive charge. The electric field that we've drawn is the overall electric field of both charges. Mathematically, this is obtained by adding. Since the electric field at any point in space can be represented as a vector, and vectors follow the superposition principle, we can just add the individual fields of each charge. Also remember, when finding electric field, we're finding the field at a point in space. You don't find the electric field on another charge. On the other hand, when we're finding the electric force, we're finding the force on a specific charge, not the force at a point in space. You can't find the force that would be on a charge if it were placed in this point in space, because you need to know how much charge is placed there. It will change depending on how much charge is placed at that point. Okay, so electric field is at a point in space, electric force is on another charge, so we need to make that distinction. Now let's look at expressing the direction of the electric field of a point charge mathematically. With electric force in the last video, we put in the direction by hand because it depended on both charges, but the electric field of a point charge only depends on that source charge. We can write the magnitude as we have before and use a unit vector to express the direction. We'll call this the vector r hat, and it will point from the source charge to the point where we want the electric field, to the point in space. If you need to brush up on unit vectors, you can go watch a video that I made on it and come back. It'll be a little bit useful. Here we won't use absolute value bars around the charge Q, and this solves our problem. Using a unit vector that points away from our source charge means that if Q is positive, the electric field also points away from the source charge. If Q is negative, then the negative sign just essentially reverses the direction, making it point toward the source charge. I won't go into any examples in this video, but finding the electric field from multiple point charges works the same as the force in the last video. Add up the field due to each charge, being mindful of the direction, and if you're working in 2 dimensions, you need to get the x and y components as needed, just as with any other vector problem. That's it for this video. In the next video, we're going to talk a little bit more conceptually about charge and types of materials so that you can really have some intuition for what's physically going on, and then we'll move on to energy, which, if you remember from Physics 1, energy is a scalar rather than a vector, so it makes solving some problems a little bit easier since we won't have to worry about vector components. So stay tuned for that, and I'll see you in the next video.